Hello and welcome everyone. My name is Jessica and it's my pleasure to introduce you here today to our event Breathe Easy, Practicalities and Pitfalls to Upgrading Ventilation in Educational Spaces. I'm going to be joined here today with Jayme Caruso. He's a vice president at SBI. They are experts in advanced learning environments, and also Jason Wilbur, who is a president at Omni CleanAir, where their mission is to eliminate the illnesses caused by unhealthy air. A little bit of housekeeping before we get started. You'll find there's a chat box over on your right-hand side. You can go ahead and enter your questions throughout the presentation, and we will get to them at the dedicated question and answer session at the end. And if for some reason we are unable to get to them, we'll be sure to follow up with you one-on-one. This presentation is being recorded, so following the event in a couple of days, you'll receive an email with all of the different links and educational pieces that we're highlighting, as well as actual replay of the event itself. And with that, I'm going to go ahead and hand the floor over to Jayme.
Morning, everybody, and thank you for your time. As Jessica said, I'm Jayme Caruso. I'm the VP of Sales for Saxton Bradley. When COVID hit us in 2020, like most Americans, we had no idea of how the pandemic would affect the country, let alone the educational environments that we particularly work in. Many schools were caught unprepared to enroll a virtual curriculum at this type of scale. Teachers had to learn new ways to teach, and IT departments had to struggle with infrastructures to equitably support a newly remote student body. In 2021, we didn't really see much relief, and it became very apparent that the effects of this pandemic were going to be long lasting. And it brought several challenges to the forefront. First and probably most effective was the lost educational days. UNICEF said that 168 million children globally had been completely closed out of education for a year. So schools closed is just a tremendous amount. The advent of masks becoming kind of the new norm brought issues with communication as teachers struggled to project and people struggled to hear their voices and to be able to communicate themselves effectively. The NEA kind of states that teachers already were more than twice as likely as non-teachers to have voice problems and 3 times more likely to see a doctor for this issue. And masks just really compounded that. On top of that, there were several studies that came out just illuminating the effect of poor air quality in general. One that was poignant, stating that it didn't just affect student health and well-being, but it also affected the learning capacity through concentration loss, tiredness, and fatigue. So we kind of looked at this and became pretty interested in how this was going to affect the environments that we as a company furnish. As we dug into it, we understood that there were some facility challenges that came around this as well. MERV 13 filters seemed to be the best option, but many environments didn't have HVAC systems that were capable of handling these filters, and it forced them to use less than ideal solutions. The systems had to be recalibrated for additional efficiencies. So sometimes these units would be running for hours before, hours after school. And that came with an increased utility cost and wear on the system. And really all this was to accomplish a simple goal: replace the air in any given space. Additionally, we can't overlook the potential trauma that's posed to returning students and faculty. The National Child Traumatic Stress Network created a report called Creating, Supporting, and Sustaining Trauma-Informed Schools, a System Framework. And this was to consider, in the time of COVID, how schools could adapt or transform their practices by using a trauma-informed approach to help children feel safe, supported, and ready to learn. And we were kind of interpreting this as choosing a strong and transparent solution that meets criteria that are both cosmetic, visible, and functional. Actually, increasing air exchange could help install confidence, and that can in turn reduce anxiety, which could lead to help with retention of teachers and assets, as well as student attendance. Any solution that you bring out there should be timely, though, and it should also look beyond the immediate needs so that it adds value throughout any process. Now, we were able to sit in on a White House symposium in which they talked about air exchange rates and how important part of the picture it was, and not just for the current pandemic, but possibly even the reduction of what would seem like, by today's standards, normal occurrences, say the annual flu. The brief went on to kind of explain that additional units in places of high aspirations, gyms, music rooms, cafeterias, performing arts centers, lecture halls, places where people are being vocal and in a tight confine, could actually benefit from having additional support. This led us, as we started looking into it, and trying to gain an understanding of what we didn't know. There's no doubt that having increased air exchange in a confined space would make sense. And it kind of seems simple, but as you start looking into it, you start wondering, what is the ideal exchange rate in any given space? How do you deal with it when your HVAC system really is maxed out? Are there supportive in-room solutions? How do you vet those through? How do you understand some maybe new jargon for us to understand, and how do you do a comparison to make sure that you're getting something that actually is functional? So from our standpoint, as we tried to understand this matter, we realized we needed a subject matter expert. So we reached out to Omni CleanAir, which is a leading provider of commercial grade and protective equipment and air purifiers. So in a few seconds, I'm going to introduce Jason Wilbur, who is the president of Omni Air Clean, so we can discuss some of these topics. And it's with this hope that we'll come away with this dialogue with a better understanding of options, how to evaluate them, and prepare yourself for possible next steps. That way we can help improve that air quality and create a more holistic environment that creates a healthy place for staff, peers, and students. Some of the things that Jason will talk about today is why do ventilation and indoor air quality matter, what the case for engineering controls is about, case for in-room portable HEPA filtration. He'll touch down on a case study to show you that in action, and then at the very end, we'll provide you some additional resources. So to that, I'm going to go ahead and introduce Jason, and we hope you find value in this.
Yeah, thank you, Jayme and Jessica, for that great introduction. As they said, my name is Jason Wilbur. I'm the president of Omni CleanAir. For over 3 decades, Omni CleanAir's mission has been to eliminate the illnesses caused by unhealthy air. And today, what I'd like to do is just share some of that experience and knowledge that we've gained, not only over those 3 decades, but over the last 2 years of this COVID-19 global pandemic, which has certainly shifted the landscape for many of us. I want to refer everyone to what I think is an incredible resource on this topic. The book by Dr. Joseph Allen and his colleague John McComber, called Healthy Buildings, Indoor Spaces and How They Drive Performance and Productivity. This is a really good resource on the subject, quite detailed, goes beyond air quality into other aspects of a healthy building, but certainly air quality plays a central role. And they really talk about why this should be an important topic, particularly in education. For us in general as humans, we spend on average 2/3 of our lives indoors, which makes it kind of ironic that we spend a lot of time when we think about air pollution about being in the outdoors. And while that certainly has negative health effects, the health effects of the air we breathe indoors is arguably much more critical. As a data point, the average student is going to spend 15,600 hours inside school buildings before they graduate from high school. And there are hundreds of studies that have been done, probably thousands, on the effects to educational outcomes and health outcomes of air quality. But a couple of notable things. There was a study that showed clearly that attention declined precipitously in poorly ventilated classrooms for students. In a study of sixth graders, the poor ventilation led to increased respiratory illness and absenteeism. I think there are other studies that show that absenteeism among staff is also negatively impacted by poor air quality. Fifth graders, similarly with poor ventilation, scored lower in math, reading, and science, which would make sense if their attention's depleted and they have more absenteeism and more illness issues. And finally, just in general, indoor pollutants like pollen and chemicals and rodent droppings and all kinds of nasty things clearly lower lung function and increase allergic reactions among students. Now, the interesting thing about this resource, while this book was published early in 2020, just after the pandemic had started, it's clear that the case that they make for the importance of ventilation and indoor air quality was really built prior to the world even knowing about COVID-19. But COVID-19 has been our reality, and it really took advantage of the state of our indoor spaces and maybe some complacency that we've had as a society around this issue of indoor air quality. COVID-19 is transmitted through the air. I don't think there's much debate about that anymore. An infected individual, as they cough, sneeze, breathe, and exist in indoor spaces, is going to emit small, light, aerosolized particles that are going to hang in the air for long periods of time and remain infectious. In order to transmit any infectious disease through the air, there's really a couple of key aspects. One is viral load, how much concentration of that virus is in the environment. And the second is the duration of exposure. And in an underventilated indoor space, both of those variables is going to be exacerbated or increased, increasing the likelihood of transmission. It's not just about COVID, as I spoke to previously. There's lots of health benefits to better ventilation in indoor spaces. But COVID-19's clearly put an exclamation mark on the need for addressing this problem. Now, if you're of the mind that, we just need to kind of hold off, wait it out. Eventually, COVID's going to move into an endemic phase or potentially disappear altogether, and we can go back to the previous normal. And while maybe it wasn't perfect, things will be just fine. I would argue that the regulatory framework here is probably going to insist that or influence that many building owners and facilities managers and stakeholders take action. You can see on the right-hand side here a number of the logos from different organizations that are going to influence what the future landscape for regulations and standards looks like. There are, OSHA is already speaking about publicly about increasing indoor air quality standards to enhance worker safety. And that will go beyond sort of the nasty industrial environments that they've focused on in the past to just general office buildings and educational environments. There are a number of organizations, including LEED certification, which used to be all about sustainability and impacts to the environment, and is now focused on health of building occupants. The UL Healthy Buildings Initiative, WELL and FitWell. These organizations are trying to create certification standards to make it clear what good looks like in a healthy building environment. There are some existing standards out there and guidelines. The state of California has a requirement in conditions where wildfire smoke has inundated a community where public buildings have to close off outdoor air completely. They can't let any outdoor air through their HVAC systems into the building. That dramatically reduces ventilation rates and creates a significant challenge, particularly in the midst of a pandemic. Another thing worth noting, most buildings that exist today were built under the ASHRAE standards, and they set minimum standards for ventilation rates in facilities. Minimum standards doesn't actually mean healthy standards. It's a minimum, and the other challenge I think we're realizing is that over time, buildings generally don't maintain that minimum standard due to lack of maintenance and attention. The air quality in buildings tends to degrade over time, not improve. The other thing I would argue from a educational perspective, in particular with higher ed and K through 12, is that that's an environment we're likely to put more regulatory emphasis behind as a country and as a society than not. In addition to places like hospitals and communal living facilities, education is certainly going to be a focus. So I'm going to transition to talking about the case for engineering controls. There's different approaches to addressing this risk that we faced prior to COVID, but certainly has been exacerbated because of COVID. This diagram comes from a guidance document from the Association for Industrial Hygienists, American Association for Industrial Hygienists. And it talks about the hierarchy of controls in order to reduce the risk of transmission of an airborne infectious disease. And on the left-hand side, you'll see a scale from the least effective approaches to risk reduction to the most effective. And on the most effective end of the scale, you have elimination, which is complete social isolation. Not terribly practical, certainly in the Western world. China, I suppose, has tried to approach this a little more aggressively, but I think the results would suggest it's not terribly effective because it's not practical to completely eliminate contact. On the least effective end of the scale is PPE, like mask wearing, which in our polarized and politically charged environment has become certainly a challenge. And both PPE and administrative controls, which would be things like staggered work schedules and hand washing and working from home, those can be effective, but everything in those two areas relies on compliance from human beings, which tends to be a bit unpredictable. Which is why engineering controls tend to be a place where professionals will migrate as they try to figure out how to really reduce the risk in this environment. Machines are generally not controversial as long as they're not too obtrusive. They're going to run in the background. They can always be on. They don't get distracted or sloppy. And they also provide a sense of comfort depending on the type of engineered control that's implemented. If it's visible in a space, it's going to provide a clear indication that something's being done to protect the health and safety of the people in that room. Now, there are other alternatives to engineered controls, certainly that have been tried throughout this pandemic and throughout history. I certainly have seen a number of folks decide just to do nothing. I refer to this as hope as a strategy. And you're rolling the dice. It may work out, but it could have dire consequences. So I suspect that if you're on this webinar, you're probably not in that camp. The second alternative is to open windows and doors, which is actually a very good idea, and where practical makes all the sense in the world. Not all indoor spaces have windows and doors to open, but if they do, it also depends on the environment outside as to whether that's a good solution. Obviously extreme temperatures of cold or heat can make that less comfortable for the occupants. And the air quality outside is not always better than the air quality inside. I used the wildfire smoke example earlier. That's one, but in urban areas, oftentimes the pollution can be bad, or you can have a bad day of pollen count, and that can create challenges for people with allergy sufferers. So that leads us back to engineered controls. And there's three main categories that I'm going to talk about today. There are a few others, but I'm going to focus on these three. As Jayme mentioned, upgrading an HVAC system is certainly a viable alternative. And I'll talk a little bit more about what some of the challenges are with that approach. There are many new technologies being marketed today around the world. It's quite a crowded space for people claiming to have been able to solve this problem that the world has faced through COVID. And a number of those technologies are what I would call active technologies. And I'll talk a little bit about how to scrutinize some of the claims in those areas to make sure that they do what they're claiming that they can do. And finally, what's been a very common approach amongst large institutions in particular is installing portable in-room HEPA filtration. And we'll talk about the alternatives in this category that exist and how to distinguish what might work in a given space versus another alternative. On the question of upgrading the HVAC system, on the surface, there's a lot to like about this alternative. In most buildings, the HVAC system does exist. There's not always in older buildings. Sometimes there is no HVAC system. Here in the Pacific Northwest, where I'm located, the climate is such that you can get away most of the year without an HVAC system. But in most cases, it will exist. And if you can upgrade to a higher efficiency filter, like a MERV 13 filter, then you have an opportunity to upgrade the system and take care of the entire envelope of the building in one go, which is certainly compelling. Many facilities managers and building owners know their mechanical and HVAC experts and contractors, and they trust those individuals. And so there's also the advantage of working with people that you know and trust. But there are some challenges. HVAC systems, in order to be good at providing ventilation and better air quality, have to be running in order to be pushing the air continuously through those upgraded filters. And HVAC systems typically aren't designed to run 24/7, 365, which can definitely drive up your maintenance costs. In addition, if you're running it that frequently, oftentimes the recommendation is to increase the percentage of outdoor air that is brought in through the HVAC system, which will increase the ventilation rates, but depending on the condition of that outdoor air, can require a lot of energy to either heat or cool or dry out the humidity of that air to protect the building envelope. Additionally, the upgrades can be quite expensive. They may require permitting or other, involved construction project aspects that can lead to a long-term project, which means you won't get the benefits of those upgrades right away. And then finally, there's this issue of split incentives. In typical real estate, there is the owner of the facility, the occupier of that facility, and sometimes even the person or the group that operates and maintains that facility can be different entities. And, it's not always clear who's going to pay for these types of upgrades and who's actually going to benefit from them. So a number of challenges. If it can be done, if it's feasible, it's certainly recommended to increase the efficiency of your HVAC filtration system. But you're probably going to have to supplement that with some additional measures to truly improve the indoor air quality and ventilation rates across your facilities. When it comes to those active technologies that I spoke of earlier, and just the landscape for selecting solutions to improve indoor air today, unfortunately, it is a buyer beware situation. I'll list a couple of terms that you'll see quite frequently, like patented or NASA technology, or aerospace materials, or HEPA-like, or super HEPA. You name it. These are generally vague marketing terms that really lack substance on the surface. There may be substance underneath, but I would strongly encourage people to go through a rigorous vetting process first in looking at the claims and trying to determine what actual scientific evidence exists that backs up those claims. If there's testing that's been done in a laboratory, even if it's been an independent laboratory, was the testing done in a vessel the size of a shoebox that claimed to disable or kill the virus, and therefore it works in a shoebox, so it's going to work in my 4,000 cubic foot classroom? If you're not sure, I would test that solution in the environment and work with the manufacturer on how you're going to measure that it's actually doing what it says it's going to do. Not all of these technologies are bad, but there's a lot of snake oil out there, unfortunately, and just encourage people to be diligent. So we'll talk about the case for portable filtration. There are a couple of technologies which are what I would put in the tried and true category that have been around for decades and clearly do what they say they're going to do. The first is HEPA filtration. This technology was developed in the middle of the 20th century and has proven to be effective in removing particles and pollutants and pathogens from the air. The other is ultraviolet germicidal irradiation, or UVGI, or UV lighting. I'm not going to talk in detail about UV in this presentation, but what I will say is UV is effective the closer you get the treatment zone or area or air or surface to the UV light itself. There's a law of the square of distance away from the UV source that determines how much energy is impacted on those biologic materials. And so in the case of some portable HEPA filtration devices, there is a UV option. And the advantage to that is that you're bringing the air close to the source of the UV intensity. But HEPA filtration is really what I want to focus on primarily, because it is, in my view, the kind of leading technology for dealing with indoor air quality where it's needed most. This slide has some data from some testing that was done in a typical conference room. All you need to do this type of testing is a portable HEPA filtration system and a particle counter, which you can see in the photo there. And the particle counter essentially counts particles in the air. In this case, in this graph, we're looking at the 0.3 micron size particles, which are many times smaller than the thickness of a human hair. And the quantity of particles is basically the number of particles counted in a minute within a cubic centimeter of volume. And the red line shows that without this portable HEPA filter in the room, just relying on the standard HVAC system, the particle counts throughout a typical day are gonna grow over time as people come in and out of the space, disturbing the carpet, disturbing the environment in general. In this case, you see a little bump as the HVAC system turns on. So in this particular facility, the HVAC system actually contributes to poorer air quality because it doesn't have high efficiency filters, and my guess is the ducts haven't been cleaned in a long time. There was then a simulation of an event, which is like people coming in and coughing or sneezing, which creates a dramatic spike in particles. And then unfortunately, with the HVAC system alone, it takes a long time for those particles to dissipate. After 30 minutes, you still have that spike has only dissipated by half, and you're still at quite an elevated level. Contrasting that with the same facility, similar activities, and a similar simulated event with a HEPA filter in place, and you see dramatically less particles. When the event happens, the peak is about a third the peak without the filter system. And most importantly, the duration of that peak, within 5 minutes, almost 90% of those particles have been removed from the space. So again, as we think about transmission of an infectious disease, viral load, and duration of exposure, the HEPA filter addresses both of those situations in a remarkably good way. When we look at the HEPA filtration options for portable in-room solutions, there's 3 categories that I tend to focus on as I kind of look at what's available in the marketplace. Industrial systems have been around for decades. They are used in high-stakes, dangerous environments, in asbestos, mold, and lead abatement projects in construction, nuclear facility decommissioning, and even patient isolation in healthcare settings. If these systems don't work, somebody is likely to be negatively affected in a severe way from a health perspective. Consumer systems have been around for a long time as well. They tend to be less expensive than the industrial systems, and they're designed for residential consumer applications. They do often contain real HEPA technology, but as I'll share in a few minutes, there are some very distinct differences between consumer systems and the industrial or the commercial systems that I'll talk about next. On the commercial side, these are really systems designed for a typical commercial facility or school, everyday workspaces and learning spaces. So they're not industrial, they're not consumer. They marry some of the best features of both of those previous categories to something that's suitable for solving this indoor air quality challenge broadly across academia as well as indoor spaces in general. The features that generally are most important, the single most quoted specification for a system typically is going to be CFM, or cubic feet per minute of air that runs through the system. This generally translates to how big of a space can I put this device in and achieve the air changes or exchange rate that Jayme mentioned earlier in this space to achieve the threshold of air quality that I'm looking for. I'll talk about the difference in systems from a sealed HEPA and filter change perspective in a minute. But the other key things are, is the system designed to run all the time? Is the footprint and the aesthetics of that device appropriate for the environment it's going to be in? I will tell you, most industrial systems don't look that attractive. It's not a high priority for an industrial system to look good in sitting in a classroom. And finally, is the system going to integrate easily into the facility's operational cadence that's typical within a school building or a large commercial facility? If you're going to have multiple devices throughout the facility, can you add an asset ID tag? Can you create a tamper-proofing user interface so that just somebody off the street can't start messing with the settings on the unit? Number of things that will be useful in that commercial or educational setting. So I talked about commercial systems and industrial systems tend to be more expensive than consumer grade systems. And there's a couple of key reasons for that. And the first is the filter size itself. Most consumer systems are going to have a smaller HEPA filter. They generally are going to have smaller CFM, or cubic feet per minute of airflow. But what we've seen with the pandemic is people have really stretched their claims about CFM, even in the consumer space. One of the big trade-offs with a smaller HEPA filter is it's going to have to be replaced far more frequently than an industrial or commercial grade HEPA. You can see the difference here with a 12-inch deep HEPA on the left versus a 2-inch deep HEPA on the right. If you're having to change that 2-inch deep HEPA every 3 to 4 months, versus on the left, that filter will need to be replaced every 12 to 24 months. And that might not be a big deal if you only have 1 or 2 machines, but if you have hundreds of machines, that becomes prohibitively expensive in terms of facilities and maintenance costs. The other key thing here, or the trade-off, is that it's almost counterintuitive, but it's easier to push air through the larger filter with more media because there's more filtration openings for the air to flow through, the larger the filter. So if I'm trying to save cost on my consumer grade device, and I also care about CFM, and I've got a filter that's harder to push air through, I don't want to increase the power of my motor and blower or fan to push that air, because that'll be more costs. But I don't want to go to a bigger filter because that's also more cost. So what do I do? Well, what they typically do is they create filter bypass. So I can claim still a relatively high CFM performance, and I have a 99.97% HEPA filter in the machine. So I've got it all. The problem, of course, is that not all of the air is being filtered. This actually is what led to some consumer protection requirements for manufacturers in the consumer space to start talking about clean air delivery rate, which is forcing them to claim to acknowledge how much of the air going through the system is actually going through the filter. And the easiest way to identify this is if a system has, say, a 500 CFM rating for cubic feet per minute through the system, but only a 300 CFM clean air delivery rate, then it tells you that 40% of the air is bypassing the filter on each pass. Now, again, for a consumer system that is concerned with pet dander and dust and mites and allergens, It's not ideal, but it's not a terrible trade-off. And in a right size space, this product can work just fine. For an industrial system, this would be impossible to deal with because the high stakes environments that those systems are used in are highly regulated, and you simply wouldn't pass muster. In the commercial industrial systems that I'm familiar with, the HEPAs are always sealed. And so the CFM performance and the clean air delivery rate performance essentially one and the same because all of the air has to go through the filter. So this is a big distinction and explains why there is a cost difference in these systems as well. Just to finish up on some of the other considerations when looking at portable HEPA filtration devices. The first is location. If you have a larger facility, multiple classrooms or spaces where you need to decide where to place units, you should certainly consult with the manufacturer. They should be able to help you determine the optimal locations. In my own experience, in a given space, the location of a machine, as long as it's properly sized for that sized room, is not going to have a huge impact on its ability to increase ventilation rates and clean the air. But some expertise can be helpful here. If you have the ability to monitor air quality in the way of VOC measurements, it's certainly recommended. It's a good indicator, particularly as occupancy goes up. As to the air quality in a space. And you can consult with your HVAC and mechanical systems experts on that. Noise should not be underestimated, particularly in an educational environment. A combination of mask wearing plus noisy filtration systems in a classroom can certainly be detrimental to the educational outcomes that we're trying to achieve and enhance. I encourage folks to test the units that they're looking at in their environment so they know exactly how it performs. Noise is a bit of a subjective measure. And power draw. The systems do use electricity, and if you put too many high draw systems on a single circuit, you may overload that circuit. So your electrician can certainly help with this. Many good systems, both commercial and consumer, are going to only draw a small amount of electricity and won't be an issue. But for an industrial system, sometimes this can become a problem. And maintenance costs obviously are something to consider and to work closely with your maintenance team on. You want this to integrate seamlessly into as many of the procedures they already have in place as possible. And the final thing I'll mention is communications to stakeholders. As measures are taken to improve indoor air quality and ventilation, I find it super important to let people know what is it that these devices are actually doing. Why are they here? How are they helping protect health and safety? And why should I want to see this continue to operate in my facility? I'll close my comments with a brief case study that we were involved with Louisiana State University. Back in the summer break of 2021, as LSU was preparing to try and get students and faculty and staff back to campus for in-person instruction, they put a task force together with the goal to find the most effective and efficient way to achieve at least 4 air changes per hour in all of their key academic spaces. So you can see here classrooms, auditoriums, and their student clinic areas, and many others where they wanted to deploy solutions. This task force was cross-functional, and they spent months evaluating numerous solutions to try and find the right portable solution that could be put in the most critical areas, because not all of their spaces were going to have high occupancy, nor in some cases, the spaces were already well ventilated. And so after that evaluation, they selected 2 units to deploy across campus. A total of 660 machines were purchased, 580 were distributed around campus, and the others were held in reserve for incremental needs. And in terms of the other priority that they had, because they wanted this in place before the first day of students getting back to campus for the fall term, they needed to select a supplier that could deliver that in under 10 weeks. This was a successful rollout. They hit their timelines. There were certainly no broad situations of COVID transmission on campus that were publicized. I think the faculty and staff generally responded favorably, and as well as the students. The one lesson learned here goes back to communication, because they did recognize early on that they hadn't done a great job of explaining to all the stakeholders what these devices were, how they worked, what they were doing in the indoor environment to improve health and safety and reduce the risk of transmission. So as a second step, we deployed some clings or posters that were applied to each of the machines that clearly stated for people in that space what they were doing. We also rolled out some enhanced user interface features to make sure that the systems couldn't be tampered with or settings changed unintentionally, because the facilities team had a very strict policy on running these machines at the appropriate levels to achieve the air changes and exchange rates that they had set out to do. So with that, I'm going to just talk briefly about some resources. You will get an email after this event, and it will refer you to some links that I think you'll find very helpful. The first one is the Upgrading Ventilation in Commercial Buildings and Schools, the definitive guide. This will cover much of the same ground that we've covered in this webinar, but in a bit more detail, and I find is an excellent resource for folks that are trying to figure out how to navigate this current challenge. And then there's a number of other links to the CDC, ASHRAE, and also to a page on our website, which we've just taken the step to consolidate a lot of useful, helpful links and articles on this topic that hopefully can help people make better decisions. So with that, I will turn it back over to Jessica to see if we have any questions.
Great, thank you. Again, feel free to send in any questions that you may have. I have a couple here. First of all, we have a question on maintenance requirements and replacement filters. Can you talk a little bit more about that for us?
Yeah, absolutely. So as I said earlier, for most commercial and industrial systems with a full kind of 12-inch deep filter, the requirements are going to be every 12 to 24 months to replace that filter. Good systems will generally have an indicator that measures the pressure drop across that filter and will actually tell you when it's time to be replaced. I will say in the case of LSU, they have made the determination that they're going to replace filters every year during the summer when the campus is much quieter. And in fact, they're going to start that process here shortly for the 2020, getting in preparation for the 2022-2023 school year. As I said earlier, for other systems, that frequency of filter changes may be much higher, and certainly something to consider. In terms of maintenance of the system in general, because industrial systems are designed and have to run 24/7, 365, And because high quality commercial systems generally operate under the same principles and using the same technology, these systems should not require much maintenance at all. The device is really designed to keep running and keep protecting the occupants in that area. So,
great. We have another one here about federal funding. Can we use federal funds like ESSER to acquire these units?
Jayme, why don't you jump on and answer that?
Yeah, sure thing. So there is a link. I think do we have that link available for the EPA White House symposium?
Absolutely. We'll make sure we send it in the follow-up email.
Yeah, so if you go on to the EPA site that we'll include with this, there actually is a statement which says under the Biden administration that there are federal funds available for this. You will have to obviously look at your path as to writing for the grant, et cetera, to get that, because that changes state by state and entity by entity as to how that works. But it is available for federal funding.
And I think the avenue in most states is through the state educational agency, whatever that might be.
Okay, and then the final question is around sound. How loud are these units? I know you touched on that a little bit, Jason, but can you talk about it a little bit more?
Yeah, of course. Sound can vary, particularly if you look at smaller consumer grade devices that are used in homes versus industrial devices that could be moving thousands of CFM cubic feet per minute of air through the system. For the commercial systems that I think are most relevant for an educational environment, the CFM performance is generally going to be somewhere between 40 decibels, or sorry, the noise performance is generally going to be somewhere between 40 decibels and 65, 70 decibels at the high end. In an education environment, I would suggest people look for systems that are below 60 dB under most operational conditions. 60 dB tends to be conversational noise level, which you don't want to be drowning out conversations in an educational setting. But again, noise is a very subjective measurement, and not all noise can resonate in the same way. So a 55 dB sound out of one device might be perfectly acceptable, and that same noise power or dB out of another device might be problematic. So testing these devices in your environment is certainly recommended.
Great. Thanks, everyone. So again, a big thank you to you, Jason. Thank you, Jayme. We're going to go ahead and conclude this webinar event. But as we said, please watch your inboxes for your email with all the different links and PDFs and resources and guides available to help you as you try and navigate this space. As always, you can follow up with us at saxonbradley.com or omnicleanair.com. Thanks and have a great day.
Thank you. Thanks, everybody.